Hi, I'm Atul and I'm an online tutor based in London right now.
Hi, I'm Paul and I'm a chemistry tutor based in Burnley, Lancashire right now. So today we're going to have a look at calculating relative atomic mass. In this case, the relative atomic mass of boron. And the question says we've got a sample of boron that contains 20% of the boron-10 isotope and 80% of the boron-11 isotope. So we can do this visually. We're just going to change those percentages to ratios in the first case. So 20 to 80% as a ratio is 20 to 80. If we divide both of those by 10, we'd get 2 to 8. And 2 to 8, if we divide both of those by 2, we'd get a 1 to 4 ratio. So we're going to show that there's a ratio of 1 to 4 boron 10 to boron 11 isotopes. So initially, Atul, could you show us a boron 10 isotope, or the nucleus of a boron 10 isotope?
Okay, so I'm going to make a nucleus of boron 10, this isotope. And just to remind that what these things are, this is a symbol for proton, red, neutron, blue, and electrons we're not using. And I'm going to make an empty nucleus first. And I'm going to fill this with protons and neutrons. So we've got 5 protons and 5 neutrons. Put that there. And so that's the 5 protons and 5 neutrons, giving us a total atomic mass of 10.
Excellent. So could you do the same again for the boron 11 isotope?
Yeah. Okay, so here's a copy of the old one. Put that back. We're now working on boron 11. Boron 11 has 1 more neutron. I'll place that there. So it's got 6 neutrons and 5 protons. Boron 11 and boron 10, 5 protons and 5 neutrons.
Excellent. So we've now got boron 10 and boron 11 isotopes, or the nuclei of boron 10 and 11 isotopes. And as we said previously, we've got 20% of boron 10, 80% of boron 11, which is a 1 to 4 ratio. So I wondered if you could show us that 1 to 4 ratio to help us calculate this relative atomic mass.
Yeah, sure. So let's get the boron 10 first. I'll make a copy of that. So boron 10 and a lot more of boron 11. Okay, I'm just going to make them a little bit smaller so we can work with them. Boron 10. All right. So boron 10, boron 11. What do we know about boron 11? 80%, it's the one that's more. 4 of those and 1 of that. So I'll be very literal with this. 1 of that. And 4 of those. And I can also just be clear that this is a 10.
Excellent. So we can see there we've got 4 boron 11 isotopes for every 1 boron 10 isotope. And to work out the relative atomic mass, we want the average mass of these nuclei. And so to get that, we just add all the particles of the nuclei up, the protons and the neutrons, which give us the mass, and divide by how many nuclei we've got here, which is 5. So rather than add up all the blue and red dots there, we can see that there's 10 in the first isotope and 11 dots in the next 4. So we just add up all those protons and neutrons, 10 plus 11 plus 11 plus 11 plus another 11. And if we add all that up, we've got 10 add 4 11s are 44. So 10 add 44 is 54. And we've got 1, 2, 3, 4, 5 nuclei. So 54 divided by 5 will give us...
We got 10.8.
So our answer for the relative atomic mass of boron is 10.8, using the ratios of the masses of the isotopes. But we were given this in percentages, so is there a way that we could have done this using the percentages of the isotopes?
Yeah, absolutely. And this is just a little bit of maths, but percentages and ratios are just two different ways of looking at essentially the same concept. So if we were to go back to percentages, it's essentially saying we've got a 20 to 80 ratio, and so you can work that out using just the percentages. I can even write it out as 20% to 80%. We got 20% of boron 10 and 80% of boron 11. And if we were looking at a 100 of these nuclei, we could do the same calculation as a percentage proportion. So that would be 20 out of 100 of these. So I'll be quite literal with that. 20 out of 100 of a mass of 10 added with 80 out of 100 in a larger sample of 100, with each nuclei being 11. And if you do this calculation, you'll end up with the same answer of 10.8. So the great thing about this percentage calculation is that, of course, we happen to have got a 2080 percentage abundance, but quite often they are something like 19.6 and other decimal values, so they're not exact. You can't have them visually, so the visual representation is just there to say it's quite literally taking the ratio and averaging it out. Here what we're doing is also taking the ratio and averaging it out, but they're given typically in percentage form, so we're just considering them as 100 of those nuclei and apportioning the relevant atomic mass of that isotope to calculate what would be a weighted average of the whole element. Brilliant. Yeah, is there anything else you want to add, Paul?
Yeah, I think it's just worth following on from your calculation there. If we just work each of those out, so 20 times 10 would be 200, divided by 100 is 2. And then 80 times 11, so that would be 880. divided by 100, which would be
8.8.
8.8. And then if we add 2 and 8.8, we get the 10.8 relative atomic mass.
Yeah, it's a more explicit demonstration of that calculation here. Yeah, so that would be unitizing it. Perfect. So perhaps we can do, now that we've seen the visual representation, you can do them just with percentages, and eventually you won't need to see them visually, but as long as you understand what's happening, you can use your percentage calculations with confidence and knowing that's actually what it means. And we'll be doing a bunch of videos with those as well, just the percentages, just the isotope, and then straight into that calculation. Brilliant. Look forward to doing that, and yeah, see you on the next one then.
Okay, thanks, Hassel.
Yeah.
Bye.
Bye.